AP Calculus BC, Unit 5, Day 10, lesson. Let's see. This will be our last lesson of Unit 5 with new material in it. So this will be it. This is our last integration technique, new technique. So let's try it out. Now there's one more problem, and you guys can go ahead and try that on your own. Doable. You guys should be able to do it. But we're going to use it as sort of a comparison for another way of getting the same answer, and then we'll learn that through sort of problems that we have to use that on. So try the one-more problem. Now, assuming you've tried it, basic U substitution works very well, right? Got the x and the dx, don't want the 2. So this is going to be 1/2 square root of u du. I would change it to a power u to the 1/2. And then we're going to bump it up 1, divide by the new exponent, multiply by the reciprocal, plus c. Rewrite it back in terms of the original variable, x. And there we go. Got our final answer. Very doable. Now, we're going to learn how to do this problem a much more complicated way that you would never choose to do if you had the choice. You just do it the way we just did it. But there will be problems that we can't. So this is called integration by trig substitution. So essentially, we're going to take a problem that doesn't have any trig in it and put trig into it to take advantage of some different properties, identities of trig. Now we're going to be using these basic Pythagorean identities, sine plus cosine squared equals 1, comes from the Pythagorean theorem. And then these other versions, if you divide everything by sine, you get 1 plus cotangent equals cosecant squared. If you divide everything by cosine, you get tangent plus 1 equals secant squared. You should be able to do all these from memory. And then, of course, we can manipulate any of these and solve for another term to get another version of it. And so we are going to be using these versions of these. Now, what we're going to try and do is we're going to try and create these patterns in our integrals that don't have trig. So the a is just going to be a number. Okay, so a is just going to equal a number in these. These are just going to start kind of general here. And we're trying to get these patterns here. So 1, so we can factor the a squared out, so there'd be a 1 there, or here or here. So each one of these matches up with one of these situations. In fact, we could do other versions too. I mean, we could do sine squared equals 1 minus cosine squared instead. That would work. So there's really kind of like 6 different versions of these that we could do. But we'll just start with these ones for right now. So the first thing you're going to want to do is you're going to want to get this to have that a squared in it so that you can factor it out cleanly. So x is going to be a, and since we're going for sine here, that's the only one of these that has 1 minus trig squared is this one. It's either cosine squared equals 1 minus sine squared or sine squared equals 1 minus cosine squared. So it's got to be that. So you got to either put sine or cosine in here. So I'm going to do sine, but you could also do x equals a cosine squared. The same types of things will happen. So now if we substitute that in, we're going to get a squared minus a squared sine squared theta. And then we're going to factor the a squared out of everything and take the square root of it. So that's going to be an a. And what's going to be left inside is 1 minus sine squared. And 1 minus sine squared is cosine squared, right? It's going to be cosine squared, and then you will get a cosine theta. So that this kind of complicated square root pattern. So we could do that up here. Could just be a nice, simple trig expression that we should be able to integrate. So you could do a cosine theta. Let's see if we put it there. Now, if you have plus a number, then the only option is to use probably this one or this one. I'm going to go with tangent because I feel like tangent is less weird than cotangent. So I'm going to try and get this tangent. So for this first one, this is one of the patterns I'm looking for, or this. I'm going to go with tangent. So I'm going to say x equals a tangent theta. So you got to get that a in there. Whatever is squared here, you want that number there. You could alternatively do a cotangent theta. It'll give you a similar pattern. So I'm going to substitute. This is going to be a squared tangent squared theta plus a squared. And then we could factor the a squared out and take the square root of it. And what would be left inside would be tangent squared theta plus 1. And tangent squared theta plus 1 is secant squared. And the square root of secant squared is secant. Now, if up here, if you did all this work, you would eventually get a sine theta. And if you did this one alternatively, you would get a cosecant theta. Either way. This last one has the thing squared minus a number squared here, which is the opposite of this. So that's got to be one of these patterns. Either one. I'm going to go secant. I'm going to say, all right, well, x equals a secant theta. You could do a cosecant theta instead. And so we're going to plug it in here. So we're going to get a squared secant squared theta minus a squared equals, take the a squared out, take square root of it, and you'd be left with secant squared theta plus or minus 1. And then that would be a square root of secant squared minus 1 is tangent squared. So we get a tan theta. Alternatively, if you did it this way instead, it fits the same pattern, you would get a cotangent theta. Now, I'm probably going to focus on the ones that seem low. I feel like secant's better than cosecant, tangent's better than cotangent. I might go cosine or sine, but any of those could work. So let's see how this works. Let's do the warm-up problem, but trying to use this technique instead. First thing, you got to be able to do these from memory. So I'm going to try it from memory right now. I'm going to say, okay, well, sine squared plus cosine squared equals 1. And I don't think that's going to fit this pattern because we need the 1 here. And if we move this, we're going to get 1 minus cosine squared. So I don't think it's going to be that one. If I divide everything by, let's say I want the tangent. Let's divide everything by cosine. You get tangent squared plus 1 equals, if you're dividing by cosine, so that's going to be secant squared theta. Now, would this work? Yeah, I think this would work, right? So I'm going to go with tangent squared theta equals secant squared theta minus 1. And I think I can make that fit that pattern. Okay, now this is where the 1 goes. This is the a value. It's 5 squared. So we're going to say, let's create a temporary, we're going to substitute this expression. It's going to be 5 secant theta. And so then x squared is going to equal 25 secant squared theta. And just like substitution, I got to take the derivative of this. Dx equals 50, or let's see, dx equals, sorry. Okay. Okay, yeah, dx comes from this up here, so it's going to be 5. The derivative secant is secant tan. Secant tan. So we're going to rewrite this, and x equals 5 secant theta, right? And actually, I'm going to write right here so I have more room. So x is 5 secant theta, square root of 25 secant squared theta minus 25. Dx is replaced with 5 secant theta tangent theta d theta. So when you do substitution, you got to get rid of all the x's and replace it with all the new variable. Now, this right here, this is where you get in the 25, you're factoring it out of secant squared theta minus 1, which is tangent squared theta, right? The square root of it is going to be, so if I rewrite this, I'm going to have 5 secant. Now, we could say 25. 5 and 5 is 25. Secant squared theta, tangent theta. That's from all that stuff. And then you're going to get another square root of tangent theta, which is tangent theta d theta. And I can move the 25 out front. And so this is secant squared theta, tangent squared theta, d theta. So now we got to factor this. So any of our other techniques might be necessary here. So probably u substitution. So should u be secant or tangent? Well, whatever u is, do you see the derivative? If you pick tangent, derivative tangent is secant squared. That'd be perfect. If you picked secant, it'd be secant tan, but you have this extra tan left over. So that's not going to work. So derivative tangent is secant squared theta d theta. So that's going to replace that. That's going to be your du. So it's going to be 25 u squared du. So it's going to be 25 e to the third over 3 plus c. And then we're going to change it back. It's going to be 25 thirds. And so u is tangent cubed theta plus c. Okay. So we're doing okay now. I feel like, there was another 25 that was supposed to be right here. So that was another 5. So this should be 125. Okay, missed that. Okay, but this isn't good because we're using u substitution. This would be like leaving your answer with u's in it instead of changing it all back to the original variable. So right now we're on theta, but we really need to get back to x. So we got to figure out how to replace theta with x. And so what's going to happen is we're going to replace tangent theta in terms of x. And so we can, just to help, we could draw a simple triangle to help us kind of set this up. So tangent theta, if we go back to the original definition up here, we could say that secant theta equals x over 5, right? And secant, so then that would mean more easily to think about cosine equals 5 over x, right? Because secant is just cosine upside down. And cosine is adjacent over hypotenuse. So I'm going to make the adjacent side 5. I'm going to put the theta here. You can put wherever you want. I'm going to put it there. And so this would be the adjacent side is 5. The hypotenuse is x. And then we could figure out what the opposite side is from Pythagorean theorem. It'd be the square root of x squared minus 25, right? A squared plus b squared equals c squared. You're going to subtract the 5 squared from the x squared, take the square root of both sides, plus or minus. So that means that tangent is opposite over adjacent. And then, of course, it's going to get cubed. Okay? Now, the 5 cubed on the bottom is going to cancel out with the 125 because that's also 5 cubed. And our final answer is going to be 1/3. There's a lot of different ways you could write it. You could just write it like this if you want, plus c. Or you could write it more like this, x squared minus 25 to the 3 halves. That also works. So, anyways, let's compare that to our answer we got on the warm-up. Hey, we got the same thing. What do you think? Should we do it this way or should we do it this way? Well, if normal U sub works, don't use trig substitution, okay? That was just to show you that we could do this other way and that it gave us the right answer. The problem is that there's going to be other problems that we can't do regular U substitution on, and we're going to need this approach, okay? So let's try a few more examples. Can we do regular U sub? U equals x squared minus 25, du equals 2x dx. This isn't going to work because the x is in the bottom. So we're going to have to try, let's try this trig substitution. Now we're trying to get this pattern right here. So which pattern is that going to be? Well, we can just write these down real quick. I should be able to do these Pythagorean trig identities from memory. If we move this over, that's going to do it because this is where the 1's going to go. So it needs to be minus 1, not 1 minus something else. So it's not going to be that. So if I divide everything by cosine, it's probably going to be that. So it looks like it's going to be that because we can subtract the 1 over to the other side. Right, so this is the pattern we're going for. So to get that, x would have to be 5 secant theta. So then x squared is going to be 25 secant squared theta. Dx is going to be 5 secant tan theta d theta. So we're going to rewrite this, and it's going to be square root of 25 secant squared theta minus 25 all over x is 5 secant theta. Dx is going to be 5 secant theta tangent theta d theta. All right, now we got to try and clean it up. Hey, the 5's cancel, secant thetas cancel. This is going to give you a square root of 25 if you factor it out, and then you have secant squared theta minus 1. Right? And then this is going to give you secant squared minus 1. That's going to be tangent squared theta. And then you can take the square root of it. So it's just going to give you tangent. Right? So in the next step, square root of 25 is 5. I'm just going to put that out front. And then what's inside is tangent squared theta d theta. Okay? So it's gotten pretty simple. But like how do we integrate tangent squared? U substitution is not going to work. That's not one we've used. So we might actually have to use trig identities to do this, because if we had a secant squared, we could totally do that. In fact, so I'm going to use the same identity to rewrite this in something that I think we would have more success integrating. So this is the same thing as a secant squared theta minus 1, right? And secant squared, we know that that's the derivative of tangent. So this is going to be tangent theta, and this is going to give you a theta, right? Plus c. Okay, so we got our answer into the theta. Now for the next tricky part, getting it back into x. So this is where I usually go back to what we originally defined for x. X equals 5 secant theta. And then I can rewrite secant theta equals x over 5. And then to make it easier for me to think about, I'm going to flip it because this is the same thing as 1 over cosine, right? So cosine equals 5 over x. And cosine is adjacent over hypotenuse. So I'm going to draw a picture to help me even more. Put theta here. And the adjacent side is 5. The hypotenuse is x. So we've got to find the opposite side, which would be a squared plus b squared equals c squared. So x squared minus 25 takes square root of both sides. That's the length of that side. And so now when we go back here, tangent is going to be opposite over adjacent. So that's going to be square root of x squared minus 25 over 5. And the 5's going to cancel. But the 5 gets distributed to this. Now, what do we put in for theta? Well, up here, if you want to solve for theta in terms of x, secant theta equals x over 5. So you could do theta equals inverse secant of x over 5, or you could do cosine theta. Right here we wrote, all right, cosine theta equals 5 over x. So you could do theta equals inverse cosine of 5 over x. So one of these is going to get plugged in there to your answer, right here for theta. So either this or this. So our final answer is going to be the square root of x squared minus 25 minus 5 secant, inverse secant of x over 5 plus c. Don't forget the plus c. Or, like I said, you could do it the other way. X squared minus 25 minus 5 of inverse cosine of 5 over x plus c. You can do that instead if you want. This problem we wouldn't have been able to do with our existing techniques. This trig substitution allows us to do it, and this is our answer. Now, on the back, I'm just going to give you guys some tips about things that you might need to use more for the integration part. Once you get it all to like this, right? We had to use this trig identity, right? Here we had to use, regular U substitution. So that's a possibility, right? So just some other things to keep in mind. Don't forget about your double angle identities. Those might potentially, you might get cosine squared or sine squared in your answer. So those double angle identities for cosine are here. We use these a lot in polar. Also, you might use this. Okay, so those might come in handy. And then, so right here is an example right away. Like, how would you integrate this if this is what you got? You'd be like, well, let's change this to 1/2 plus 1/2 cosine double angle, right? And then you say, okay, well, the answer here is 1/2 plus 1/4 sine 2 theta plus c, right? So you might need to use something like that. Secant squared. Well, that one's one we've memorized. That's just tangent theta, right? So, I mean, it is possible you might just get one of your derivatives. Cosine cubed, something to consider is to rewrite it as cosine theta times cosine squared theta. And then you could use the Pythagorean identity, replace cosine squared with 1 minus sine squared, which might seem like backwards. Like usually we want to get it all in terms of one variable, but you can't integrate cosine cubed. You can't. But if we do this, we can integrate the cosine on its own. And then you get cosine sine squared. And this one we could use U substitution now. We could say U equals sine theta, du equals cosine theta d theta. And so this one will be u squared du, u cubed over 3. So our final answer would be sine theta minus 1/3 of sine cubed theta plus c. So this isn't trig substitution stuff on the back. This is just some ideas to consider when you go to try and integrate. The problems for today's homework are going to be out of our old book from last semester, last year, Calc AB. It's the white book. Anton's the author. These are the problems. They're all odds, most of them. Check your odds in the back of your book. And let's try some trig substitution. I think on these, you really got to, just, it's kind of weird. It's kind of hard to get the hang of at first, but the more of them you do and the more you pay attention to trying to take advantage of patterns and not just look up the last problem, but like really force yourself to do each one individually, you're going to start to really get a lot better at this. So try it out.